Since we're studying multivariable calculus in this class, it'd be a good idea to say at least a little bit about how this stuff works for multivariable functions. So, something we'll get into a little bit more in a later video is that Taylor series actually can allow us to approximate functions, right? So, f of x, right, as a Taylor series, we have, this is f of a plus f prime of a. I should actually not write that so weirdly. F prime of a times x minus a plus 1 over 2 factorial f double prime of a x minus a squared, and so on, right? Well, what we could do is if we cut off this Taylor series at various points, we get different types of approximations of the function near x equals a, right? So you could have something called a linear approximation, which is where we cut off at one term, or after the degree 1 term. So f of a plus f prime of a, f prime of a times x minus a, all right? Now, something neat, if you think about it, if you graph this equation here, that's just the tangent line at x equals a, right? This is a linear approximation. It's an attempt to approximate the function itself by a straight line that's tangent at x equals a, right? This is the idea behind how differentials worked, if you've looked into that before. Well, moving on from a linear approximation, what if we try to approximate the function by a parabola? Well, that's just the quadratic approximation. Let's see if I can spell that right. Right, so this is a slightly better approximation of the function. And it involves taking the Taylor series up through the second degree term. So we have all this stuff from before plus this term, right? So the graph of this is, if you like, sort of a tangent parabola, maybe? I wouldn't use the word tangent anymore here, but it hits the function exactly at x equals a and tries to fit as close as possible for, as long as it can near x equals a, right? So we could keep going on getting a cubic approximation, a quartic approximation, and so on. But I want to stop here because this is the easiest place to cut off for the Taylor series for two variables, right? So how does this work here? Well, what we get, right? So for a function f of xy, what does the stuff look like? Well, instead of a first derivative, we have the gradient, right? The gradient at, say, AB. Right? This is, let's actually write this in a nicer way, maybe. You know what? This is fine for now. AB. This is fx at AB, fy at AB. Right? And the second derivative, the sort of most general thing we have is this Hessian matrix at AB, right? And this is the matrix fxx at AB, fxy at AB, fyx at AB, and fyy at AB, right? So how can we do this? All right. So the linear approximation, let's actually do a couple things to help with some notation. right? We're going to write vector x. This is going to stand for x comma y, okay? And vector a, this is going to stand for a comma b, right? So the linear approximation, right? So this will be sort of the degree 1 Taylor polynomial, if you will, near near the point AB. So it's going to be approximately f of AB plus, right? Now the way this is going to work is we actually take the gradient of f at AB and we take the dot product with x minus a. Right? So what that looks like, this is f of AB plus, if we want to write this all out, it's going to look like fx at AB times x minus a plus fy at AB plus, or times y minus b. Right? That's what that dot product is going to look like. That's the first order linear approximation of this function. Right? Now, interestingly enough, if we graphed this, much as this one here gave us a tangent line, if we graph this one, we get a tangent plane to the function. Right? Now, how about a quadratic approximation? Right? So how does this work? Well, here's where we get into a little bit of trouble with thinking of vectors as columns versus rows. We really want to think of vectors as columns here. All right. Then the quadratic approximation, all right, is going to be much the same. Really here, I'm just going to stick with the vector notation. Say this is f of a plus gradient of f at a dot with x minus a. So far, things haven't really changed. But this next part, what is this going to be? All right. This ends up being, let's see here. We end up needing 1 over 2 factorial times, right? What this is going to be is x minus a dot product with the Hessian at a applied to the vector x minus a. All right. So if we write all that out, what does that actually look like? Okay. So this is f of a comma b plus all this stuff from before comes down. So f of x, a comma b times x minus a plus f of y, a comma b times y minus b. But the rest of it, what that is this is plus 1/2. Right? What you're actually going to see here is the following. Right? So you're going to get fxx at AB times x minus a squared, right? Plus 2 fxy. All right. Now the reason for that is fxy and fyx are the same, right? For this function, because it has to be at least, it has to be infinitely differentiable to do a Taylor series, right? So for this approximation, we want it to at least be twice continuously differentiable. Right, so I have x minus a and y minus b, and then plus fyy. Oh, we're running out of room. Let's move all this over a bit. Right, so this is fyy of ab, y minus b squared. All right. So it's a bit of a mess when you write it, when you expand it out, but it's actually quite beautiful how this works out in general, especially when you start getting on to, say, a cubic approximation, right? And the beautiful thing about this, about using this vector notation here, is we wrote this out for a function of 2 variables. You can do this for 3 variables, 4 variables, it doesn't matter. It's always, maybe here instead of fx comma y, maybe if I just write fx, all right, then if x is, this vector here stands for x comma y comma z, then this formula holds exactly true still, right? So it's kind of neat to be able to use this vector notation to sort of compress everything. And this is why vectors and matrices really make life that much easier for us, right? Now again, when you get on to third order stuff, or third degree approximations, cubic approximations, it gets a little bit trickier because, if we think about how the derivatives work, the first derivatives form a vector, the second derivatives form a matrix, the third derivatives form kind of like a cube-like thing. So it's a little bit harder to keep a nice formula like this going, but there is a certain way to do it, and I challenge you to look it up. It's really, really interesting stuff, and I'd be happy to talk to anyone about it. But with that, we'll stop this video here.